Okay, I got I got started recording, so let's get started right now. And um, so these are fairly good quality questions, so we're going to explain. And um, there are 7. So when you do this type of the counting problem, the first try to model it. There are 7 parking space in a row. So you would say that 1, 2, 3, 4, and 5, 6, and 7. And how many ways can space be assigned if at least 2 of the assigned space must be adjacent? So basically, if you really do the work, yeah, too many ways. Basically, it could be first floor occupied, and you could be like, 2 of them occupies those, and 1 of them occupies this and this. So it's really, no end for all the combinations. So basically, we trying to, if you find something that it's too hard to enumerate and it's too hard to manage, then try to look the reverse of the problem. So we know that, um, in the set theory, basically, A union the non-A will be the whole thing, basically, if we have a whole thing. So basically, we're looking at the reverse of this phrasing, the phrase. So what is the phrase? How many way can the space be assigned if at least 2, reverse of it is none of those 2 are adjacent? None of those 2 are adjacent, there are only one way, because you can only do like, 1, 3, 5, and 7. That's the 4 fixed way. So we will try to do that, then subtract from the total arrangement. And so it looks like, when you read the problem, also trying to understand the problem if it is require any distinguishable. So obviously the parking spot is labeled 1 to 7, it's distinguishable. Also the person, the 4 co-workers, those are different person, you cannot be, mistaken. So, so basically, the way to randomly assign 4 distinguished person to 7 distinguished spot, it's actually, fairly easy to understand. And this one basically is just 7 permute 4. 7 permute 4 is also basically, 7 multiply 6 multiply 5 multiply 4. Then basically we have 4 spot to arrange 4 person. And then that is actually like 1, it's going to be 4 spot, arrange 4 person, 4 multiply 3, multiply 2, multiply 1. So if you use permutation, that's going to be the way that, could be arranged. So this minus, and you will get the answer. And like, I'm going to save time, not going to use. So basically, if you, for doing statistic problem, you actually can use calculator, assuming you are using, and on the AMC, usually it's these are the classwork problem. Usually, the number is a little bit bigger, but in the AMC, it's going to be usually quicker. And so it's basically, this basically is like 7 permute 4 minus like 4 factorial. So this is Let's try to do it. So if you use TI calculator, this is the way that if you click, let me quit the mode. You click alpha, then window, it's going to show the statistic function. And this is permute, this is choice, this is the factorial. So basically, you can, after get here, you can click 7. So it's going to like 7 permute 4. And then minus, and like, you do that again. And then this is the factorial. I have to put in the number first. Let me quit it. So basically 7 minus 4 minus 4 factorial. Or alpha. And that's 9. So basically, 816. And so basically, you can also do it a different way. You can use choice first, because, if you use choose first, basically you have to choose, the way to choose just for spot, it's from 7 is 7 choose 4. And 7 choose 4, then one of the arrangement, this could be taken away. So you -1 arrangement, then these are how many tries you can make, just picking the spot. Then multiply, after you choose the spot, for example, I pick, this is not allowed. I pick those, and for example, and this is a legit arrangement, then it's one of those in this number. Then within those 4 spots, I can like to multiply 4 factorial, then you still can do this problem. So if I do it this way, then basically, you can have 7 choose 4. So 7, 6, 5, 4. And that's 7, 4 is equal to 7, 3. So basically, I think we'll just do 3. So 3 to 1. And so that's equal to 35 minus 1 is 34. 34 multiply, this is actually 24. So basically, we're also going to get a number. And so, yeah, so that's 24 multiplied 34 equals 816. So basically those two will come up with the same solution. So there are usually multiple ways to do this type of the problem, and just have to be, more consistent. Then either way you will be fine. And then let's go to this problem. This problem is still a, complement problem, because let's just go from here to here. How many way is fairly, let's rehearse this problem again. Basically, we label the instruction of going, this is the going right, this is going up. So it's a 10-step problem, 1, 2, 3, 4, 5, 6. We have to go 7 or 6 R and 4 U. So basically, basically it's just a, permutation with duplication. If you treat it this way, permutation basically it's 10 factorial divided by 6 factorial and 4 factorial. Or if you view it as a choose problem, because out of 10 instruction, you need to choose either 6 right or either 4 up. So if you view it that way, it's going to be 10 choose 4. So that's the total. Then we're trying to see how many ways that need to be subtracted from, because from going through X, and not going through X is very hard to arrange because it's just so many ways that, it's just will pull you down fairly quickly. So passing through X, then we have to go from A to X first. And go from A to X, basically it's a 4-step instruction, 1, 2, 3, 4. Basically 4-step, choose 1, 2 of the up or 2 of the right. So basically that's 4, choose 2. And then from X to B, there are 1, 2, 3, 4, 4 right and 2 up. So it's 6, choose 2. So basically, and those statistic problem in the long term, it's not about calculation. So basically it's about thinking. So I kind of just use the calculator to do it. So if I do the like alpha window, and this is the truth. So you're going to use 8. So basically I'm going to do 8 and 10 true, 10 choose 4 minus, and then do it again. So 4 choose 2 and multiply 6 choose 2. So 120. So this is 120 way. Okay, let's also check the answer because I kind of just do it. I didn't really, I copied down the answer. Yeah, so it's 816. So this is right. And 120 way. So this is, is right. So basically this is just the way that you have to do it. And so this one, let's trying to do this one. And this one is zip code in the United States, 5-digit long followed by the 4-digit. So this is the total is 9-digit. In North Carolina, every zip code begin with 27 or 28. So this is the example, like 27. And how many 9-digit zip code are possible in North Carolina in which each digit is only used once? So only used once, basically, it's like a permutation, basically. And because each zip code, with those 4 are different. So we have 1, 2, 3, 4, 5, 6, 7. So we have 7 digit need to choose from a total of 8 digit. Because, from 0 to 9, you all have altogether, you have 10 digit. And for example, 27 was occupied, then you have 8 remaining letter to arrange 7. So it is 8 permute 7. 8 permute 7, that's 4 to 7. Then because you can begin with either 27 or 28. 28 basically, it will be totally different from this. So basically it's need to be multiplied 2. So basically it's going to be a relatively big number. So I'm also going to use the calculator. So it is going to be alpha window. It's the 7th function and 8 permute 7 and then multiply by 2. So that's going to be A0640. Let's copy this. So this is the answer, 80640. So let's try to do this one. A mother, her 3 children, and their spouse are taking a having a photo taken seated on a long sofa. If each couple must be seated together and grandma prefer to sit between 2 couples, how many seating arrangements are possible? So basically the couples need to sit. So the mother and their 3 children and their spouse. And so the 3 children, they have to sit with their spouse. So spouse, we will just see as attachment. We're not going to deal with spouse first. We're just going to deal with 3 children, because once the children position was determined, their spouse will be derived from theirs. And then, so basically it's like children 1, children 2, children 3. And this is spouse 1, spouse 2, and the spouse 3. And then we have the mother. And obviously, the mother basically is the grandma, and prefer to sit between 2 couples. So basically, children 1, children 2, children 3. And so it will have 2 positions for the mother, and we will derive those after those is arranged. So just arrange the children. They are 3 factorial way, basically. So, and their mother, and for example, this is the, ABC, let's say ABC is arranged, and you have 6 ways to arrange those 3 couple. And then once a single arrangement was picked, the mother could have 2 positions, so it's going to be multiplied 2. Then basically the whole arrangement is set. So between each couple, for example, couple A, and they have child 1 and spouse 1 could be this way, or spouse 1, child 1 could be this way. So basically there are 2 ways. So for each couple, they have to multiply 2. So I have to multiply 2 cubed. So basically that's the way that can be arranged. So this is really simple, because this 3 factorial is just 6. And this is 2 to the 6. 2 to the 4th is 16. So this is, yeah, it should be 96, something like that. So let's check the answer. Yeah, it's 96. Let's do this one. And 3 friends, Al, Bill, and Carl, are painting their chest with the word Cavaliers for a basketball game, and at least 2 letters painted on each friend's chest. For example, Al must get CA, and Bill VAL. This is might, not must. So might get, and Carl is IERS. And so this is another arrangement. So Carl getting more letter, and yeah. So how many ways can 3 friends get their chest painted so that they can stand in the correct order and spell the word Cavaliers? So basically they are like 1, 2, 3 person. And the first person basically, have to get at least need to get 2. So basically, the first person need to get the first letter CA, and the last person need to get the last 2 letter RS. So we have like VA, L, I, E. So these 5 letters are up for the grab between those 3 person. And between those 3 person and this, those 3 person, Also the second person need to have at least 2. So basically, and also, the first person or the last person cannot have more than 4, because at least. So we will just have to, yeah, so basically, or at least each person has to get like at least 2 letters. So basically, we have to find out ways that, so basically, VALIE is those 5 letters. And then we use the divider. It's just like a stick and a stone problem. And we will have like 6 places to put the divider. So basically 1, 2, 3, 4, 5, 6. And so those 6 place divider and have to, hold 2 dividers. So basically, for example, I can put dividers this way. This is actually a working method. So basically, this is the first guy get CA, and the last guy get RS, and the middle guy get all 5 letter. So basically, this is a working arrangement. But some arrangement actually is not working. So basically, if I put the divider on the both end, so the first person already got 2 letters. I don't need to worry about him. And I think, the one is not working is that, the middle person getting 2 less. For example, if I put, 2 dividers this way adjacent, then it's not going to work because this way, the second person only got 1 letter. So then you can also put those 2 way, and so there are a bunch of ways you can do that. And in fact, those 2 arrows need to be adjacent to be just 1, 2 letter. Otherwise, it's actually going to work. So basically, I have 1, 2, 3, 4, 5. I have 5 ways to put arrangement not legit. Then basically, I have 6 positions to put 2 divider. That's going to be 6 choose 2. And 6 choose 2 is just 6 multiply 5 divided by 2 multiply 1. That's going to be 15. And 15 minus 5 going to be 10. So because only 2 arrows are adjacent, it won't be legit because the middle person getting 2 less. Otherwise, if you do it other way, it's going to be enough to satisfy the condition. So basically, to arrange the middle person and the rest of the person's arrangement, I have 10 ways to put divider. Then after we have 10 ways to put divider, then we also have six ways actually multiply 3 factorial ways to arrange those 3 friends, Al, Bill, and Carl, because I can, this is just an example. For example, it already gave you the example. Al might get CA, Bill get VAL. Then, Carl could take CAVV. So basically, it's just between those 3 friends who take the leading character, who take the tail character, there are 3 factorial ways. So if we multiply it out, it's going to be 60. So 60 is the total arrangement. Let's check the result. And So this problem is that elaborate code consists of left and right arrows, which are placed together to represent words. And there are spaces between the words. For example, the code of the left and the four right arrow arrangement with two space. So these are 1, 2, 3. So 3 left arrow and the 4 right arrow, 1, 2, 3, 4, and 2 space basically can make this arrangement. There obviously there are more, and represent a 3 code word phrase. So how many different 3 word phrase in this system using 8 letters? Yeah, so basically, we have 1, 2, 3, 4, 5, 6, 7. We have 7 or 8 letter. These are 7 letter. We have to use the 8 letter. So basically, you know, it's use the 8 letter. How many different 3-word code phrase in this use 8 letter? And those 8 letter obviously didn't tell you which letter is, because each position could be, each position on any of those positions, it could be left arrow or the right arrow or the left arrow. So basically, they are like 2 to the 8th factorial way to write really each position of the letter could be like 2-way. So that's how many ways you can change the letter appearance. Then we will trying to figure out how to place the gap. So you have, obviously you cannot have, so basically you have 1, 2, we will say that 1, 2, 3, 4, 5, 6, 7, 8. We have 8 letters. And we need to put divider between the gaps. So they are 1, 2, 3, 4, 5, 6, 7. We have 7 gaps. And so 7 gaps to choose the position of 2 arrows. So it's 7 choose 2. And the 7 choose 2, it's just, you know, make 3 letter. And so each word going to be a like at least a 1 letter phrase. So basically, you know, then within those tiny positions, you have 2 to the 8th factorial. So I think this will be the answer. Let's try to calculate and get the answer. And so this is going to be 7 choose 2. And let's do that. And 7 choose 2 and multiply and 2 to the 8th. So 5, 3, 7, 6. Let's check if I did it right or not. Yeah, that's right. So basically that's the way that let's do this one. And this one is Jeffrey has a set of tetrahedral dice. Each has a distinct arrangement of exact six dots, depending on the four faces. And no two dice can be rotated to appear the same. And faces can have any number of dots on each face, including 0. How many dice in a set that has distinct arrangement of 6 dots? Exactly once. So basically, this is one of the arrangement. You have 6 dots. Basically, you have the you have like 0 dot dice and 1 and 2 and 3. So basically, you can have a lot of those. And this one, let me just check the answer directly, because this one is really difficult. And let's just check the answer directly. Let's see what it's saying. This is a tricky case work. Following is the list of all the ways that dog can be placing the 4 faces. So basically, it has the 6 yeah, so basically it's actually, list out all the possible ways. And so I think let's try to figure out how it's doing the casework. Casework, obviously you can have 6 is the leading case. So if one of the dice has 6 dots, the rest must have to be 0. Then the next is like 5-1, and 5 basically you can have 5-1 or 5 like 0-1 and 0 and 5-0-0-1. But basically this is a tetrahedron shape. Basically, it's asking that no 2 dice can be rotated to appear the same. So those arrangement, basically you can rotate, because there are 4 different ways you can put the tetrahedron on a table. Basically, there are 4 faces. So if you rotate enough, those arrangement will appear the same. So basically we combine this into just one case. Then these are all the same. And so basically, we are trying to just put a leading number, and then we use an ordered arrangement. And those ordered arrangement, if we really lay it out, that's 1, 2, 3, 4. And these are 9 of those. And 9 of those, only this is the, only this one, could be arranged by 2-way. And there's a, so basically, this is a 4-letter arrangement. There are 4 factorial ways to arrange it. So it's equal to 24. And then for we to understand this, we actually have to use a model to really see it. I think we will try to do a model next time. I really haven't prepared so well for this problem. And so basically it's like flipping the chain. I know the flipping the chain, it's easy to explain. So this one, let's try to do it the next time. And so this problem is also relatively quite difficult because I actually did it once. Unlike the other problem, I didn't do it. Then I have to do it from scratch. This problem actually, I tried to do it before. So there are just so many ways that you can draw the parallelogram that, things that almost unimaginable, like really, really odd shape, you can draw it. And I don't think this is a much fun problem. I don't think, it could be a test in a like,